Hi, today let's solve finding kth node from end of a linked list. Suppose we are given this linked list, say 1, 2, 3, 4 and 5 nodes, alright? And let's say we have head marked as head at node 1 and we are given k equals to 2, meaning we want to find second node from the end. From the end, the first node is 5 and the second node is 4. So our expected answer will be 4. The problem with linked lists is we don't know their exact length beforehand. So the first thing we must do is to traverse the entire list and count how many nodes exist. Okay, so let's go about and find the length of this linked list, like how much count does this linked list have. So let's keep track of the current and the count, like how count is incrementing and how current is flowing through the entire linked list. So let's keep here as the current at the first node and keep the track of count over here. So when the current is the first node, the count is 1. You move it to the next node, the count is 2. Move it to the next, the count is 3. Move it to the next, the count is 4. And move it to the next, the count is 5. And move it to the next, the current is at the null now. So it means we have reached the end of the linked list. So the length of the linked list is 5. Okay. So now that we have our length as 5, we have the target steps from the head as L minus K. So how are we getting this? So think of the linked list as a straight line of nodes. So if the total length is L, then the last node is first from the end, the node before it is second from the end, and so on. So if I want to find the kth node from the end, that means there are exactly k minus 1 nodes after it. So out of total nodes L, if k nodes are counted from the end, then the remaining nodes will be L minus k. So instead of counting backwards, which we technically can't do in a singly linked list, we simply start from the head and move L minus k steps forward. That is why the kth node from the end is L minus kth step from the start. So in this case, we have L minus k as 3 because L is equals to 5 and k is equals to 2. So we need to move 3 steps from the head. So our job is now very simple. Start from the head and move exactly 3 steps forward. When I say 3 steps, I don't mean the third node from the head. I mean move forward 3 times using the next pointer. So that is what I mean by 3 steps, okay? So our next step would be to move forward thrice, right? So the first step will be from 1 to 2. So we have cur at node 1 and we follow the next pointer once. So we move from node 1 to node 2. So after step 1, current is pointing at node 2, right? So in step 2, we have 2 linked to 3, and now right now current is pointing to 2, right? Now this will be moved to node 3. So after step 2, that is 2 steps are done, we have current pointing at node 3. So far we moved forward twice from the head. Now coming to step 3, we have current pointing at node 3 and link to 4. So we move from node 3 to node 4. So that completes our 3 steps from the head. Okay, so we stop here because our formula told us to move exactly L minus k steps. So L minus k here is 3. So we stop it here. Okay. So once we complete those 3 moves, the node we land on is guaranteed to be the kth node from the end. So node 4 is our answer. You can actually double check it. So the last node is 5, which is the first from the end, and node before that is 4, which is the second from the end. So the brute force method works because once we convert kth from the end to L minus kth steps from the start, the problem just becomes a simple traversal problem. Okay, so let's get to the coding part of our brute force solution. Here I defined a method named get kth node from last brute force. This function takes the head of a linked list and an integer k, and it returns a kth node from the end. So let us look at the first edge case. So if at all we have a linked list that is empty, there is no node to return. Also asking for a 0th or a negative node from the end does not make sense at all. So in both the cases, we should return -1. So if not head or k is less than or equals to 0, we return -1, right? And now we should find the length. Since a linked list does not store its length, we traverse the entire list once to count how many nodes it has. So we have length initialized to 0. We have current equals head, and while current exists, length plus equals to 1 and current equals to current dot next. So we move the current pointer node by node, incrementing length each time. When current becomes none, we have reached the end, and length stores the total number of nodes. We also have another edge case to be wary about. So what if k is greater than the length of a linked list? So we can handle it like this. If k suppose is greater than length, then also we return -1. Okay, understand this. If k is greater than the length of the list, then kth node from the end simply does not exist. You can't ask for fifth node from the end in a list of only 3 nodes, right? So now comes the key conversion. So current is head, and steps to move is length minus k. We already understood that the kth node from the end is the same as moving length minus k steps from the head. Now let's move the pointer. For in range of steps to move, current equals to current dot next. Okay, so we start again from the head and move forward exactly length minus k times. Each move follows the next pointer. After completing the required number of steps, current is pointing to the kth node from the end. So we simply return its data. So return current dot data. Okay, so let's run this. Yeah, so in the first example, the list has 9 nodes and k is 2. So second node from the end is 8, which our function correctly returns. In the second example, k is greater than the length of the list. So kth node from the end does not exist, and the function correctly handles this edge case as well. So to summarize, this solution handles all edge cases like an empty list, invalid k, or k greater than the length of the linked list. And lastly, if we come to the time complexity, it is big O of n, but since we traverse the list, it is a 2-pass solution. So the space complexity is big O of 1 because we only use pointers and counters. So this solution works, but we traverse the linked list twice, right? So there is another optimized solution. So that is called the 2-pointer technique. Let's look into that now. The optimized approach, we want to find kth node from the end in a single traversal. To do this, we use 2 pointers. One is fast and one is slow. So the trick is to keep a fixed gap of k nodes between both the pointers. When the fast pointer reaches the end, the slow pointer will exactly be at the answer. Let's take the same example that we did earlier. This is the linked list we have, and we were given the value of k as 2, meaning we want second node from the end. We start by placing both the pointers at the head of the linked list as slow and fast. So these are the pointers that we place here. So at this moment there is no gap between both the pointers fast and slow. Now we move the fast pointer one step ahead. This is step 1, and we move fast one more step. Now fast has moved k equals to 2 steps ahead of slow. So this gap is the most important part of the algorithm. Like we will now move both the pointers together, keeping this gap constant. So the gap between the slow and the fast pointer is k equals to 2 now. Okay, let's make a new diagram to see the entire flow clearly. And null. So slow was earlier pointing here and fast was pointing here. So now we move slow and fast together one step at a time. So slow will come here, fast will go here one step, slow will hit here, fast will go here, move again, slow will come here and fast will hit null, which means it has reached the end of the linked list. The moment fast pointer reaches the end, we stop the traversal. Because the gap was exactly k nodes, the slow pointer is now pointing at the kth node from the end. Slow is now pointing at node 4, which is our answer. So to summarize the entire thing, we created a gap of k nodes, moved the pointers together, found the answer in one single traversal. Now that we understood it visually, let's implement this logic step by step in code. Cool. Here I defined a method named getKth node from last optimized. So this function returns the kth node from end of the linked list using an optimized one pass approach. So let's tackle the first basic edge cases. If not head or k is less than or equals to 0, we return -1. If the list is empty, there is no node to return. If k is 0 or negative, the request itself is invalid. In both the cases, we are returning -1 immediately. Now let's initialize two pointers, both slow pointer and the fast pointer. Slow is head and fast is head as well. So these pointers will help us track the positions in a single traversal. Now we move the fast pointer exactly k steps ahead. This creates a gap of k nodes between fast and slow. While doing this, we should also check if fast becomes none. Why? Because if that happens, it means k is greater than the length of the list, and obviously kth node from the end does not exist. So for in range, if not fast, we return -1. This is one of the edge case, and fast is fast dot next if that is not the scenario. So at this point, fast is k nodes ahead of slow. Now we move both pointers one step at a time. While fast exists, slow equals to slow dot next and fast equals to fast dot next. They move together, maintaining the same gap between them. When fast reaches the end of the list, that is null, slow will automatically be at the kth node from the end. So once the loop ends, we return that data stored in the slow node. So return slow dot data. So let's check the output here. As you can see, this is the output, similar to the brute force approach, but the difference is that the solution runs in big O of n with just one traversal, unlike 2 by the brute force approach. And similar to the brute force approach, it uses big O of 1 extra space. Comment on your thoughts below if you have any. Thanks for watching.